Uh, so thank you all for joining. A very good evening to you all. My name is Srinivas Tangirala. I hope you all have attended the first session on the introduction to motors. This is the second webinar titled Introduction to Finite Element Methods, FEM. And we will walk you through what FEM is, how it works with respect to different domains, including an example of structural solid mechanics, as well as heat transfer, and of course electromagnetics, a sample. So you'll understand how simulation thing works, because FEM is widely used, very popular numerical technique used in many of the simulation softwares, and we'll walk you through. So this understanding will help you do the simulations in a much better way and how to do it in a very systematic way. So, and we'll also walk you through what works behind it, how it works, the math behind it, the equations, and the physics behind it. Okay, so my name is Srinivas Tangirala. I head the computer-aided engineering tools at PiLabz, and I have a team of software engineers and domain experts in my team. And Supreet will be presenting the first half of the presentation. He'll walk you through what FEM is, the basics and all that. Then I will cover the later part of electromagnetics, finite element methods, and the governing equations for that. Okay, over to you, Supreet. You can get started.
Thank you, sir. Good evening, all. My name is Supreet, and I'll be, as sir said, I'll be introducing you to what FEM actually is, and then we will look at some examples which will be taken over by the sir. And before we start, I would like to put up a poll just to understand how many of you have heard about FEM or FEA or related terms. So I have put up the poll. You can just vote quickly. So over the course of this webinar, we will cover what FEM is, how do you model phenomena in nature, that is using ODEs and PDEs. Then we'll look at some example PDEs, which will then be solved using FEM. We'll look at what the flow of FEM is. It usually involves meshing. You have a geometry, you mesh it, you apply boundary conditions, and then internally there is something called assembly of equations. And then we'll look at some examples of application of FEM. Then we'll look at finally what is important to motor, which is electromagnetics, and how FEM helps in analyzing electromagnetic problems. All right, I see about 12 people have voted. Please do vote and keep a lookout for the polls that we'll be putting up. All right. So FEM stands for Finite Element Method, and it's a very powerful and widely used numerical technique for finding solutions to partial differential equations. So the PDE here actually stands for partial differential equations, and it's a must tool for any engineer, any researcher, because as we start designing new products, as we start exploring new phenomena, you usually represent them in what we call partial differential equations. And as we'll see later in the course, there are solutions you can explore for very simple geometries. But for problems of practical interest, you invariably need to analyze them using FEM. For example, here we have shown a set of images relating to motor. The first image is stator, where you are looking at forces as the rotor rotates around the stator. At the center of the stator, what are the forces, what are the stresses produced within the stator? Then we have an image of housing where we are looking at the temperature distribution. Then we have a water jacket which cools the housing. So for example, if natural convection or forced convection with air is not sufficient, you can add a channel where you can pass water through it and then improve the cooling. And then finally rotor, where we have shown some, again, as the rotor rotates, what are the stresses acting on the rotor. So as you can see, it's a very complicated machine, very interdisciplinary machine. which is not, if you are looking at analytical solutions, you won't be ever able to solve any problem like that. So as a result, we have FEM where you can solve problems in different fields, and you can also solve fields that are interrelated to each other, what is usually known as the multi-physics problem.
Yeah. Coupled physics. It's actually called coupling of multi-physics. Yeah. So hopefully all of you understand what a rotor is, stator is. Those of you who attended the first webinar, so you can relate the parts here. I mean, the stress analysis, the thermal analysis, and of course the fluid flow, the heat thermal transfer in each of the parts. Yeah. Okay.
So as I said, you can represent phenomena using, I mean, any phenomena that occurs in the nature, you can represent them using what we call ordinary differential equations and partial differential equations. And you may have already encountered these equations or these ideas in your undergraduation courses. So I'll just do a brief comparison of both. So if you have equation where you have only one independent variable, then it's an ODE. If you have multiple independent variables, then it's a PDE. So for example, so if you have you can look at the example given here, dy by dt equal to velocity. So y is the position, and position is dependent on velocity. So higher the velocity, the more your position change. And when it comes to notation, you have notations like d by dt of some variable. For example, here it's y. You can have a d by dt of temperature. You can have d by dt of say force, any of those things. And in partial differential equations, we want to differentiate that from the ODEs. So we use notation called a dou. So it's called dou or del, dou x by dou u, things like that. And so you can represent much more complicated phenomena using PDEs, whereas ODEs it's restricted to all the phenomena where the independent variable is only one. So for example, let's consider two examples here. One we have shown is a motion of planet. So if you look at motion of Earth around the sun, the position of XY position of the Earth is just dependent on time. It doesn't depend on anything else. I mean, of course, there are forces, gravitational forces at play, but finally, when you write down the equations, the only independent variable would be time. So such a phenomenon can be described using ordinary differential equation. On the other hand, we have shown a vibrating string, and it's going up and down, and you can look at any point on the string where the y position of that point will be dependent on where it is on the string as well as the time. For example, if you look at leftmost end of the string, it's always 0. The position is invariant. But as you go along the length of the string, for example, at the center of the string, the y position of the point changes by a large value, and it's going up and down, and it's dependent on time. So ideas like this, where you have multiple independent variables, you can use partial differential equations to represent. So let me just put up a poll. So here is a typical partial differential equation. Some of you may have seen this. It's called a wave equation. So essentially, the vibrating string that we saw in the previous slide is actually represented using this wave equation. So here u is say displacement and t is time, c square, this is speed of the wave squared, and then you have position, x is the position. So here we see that displacement u is dependent not just on time, but it's also dependent on position of the point on the string. So this is just a one-dimensional string. If you have you can imagine a plate, or you can imagine you may have seen this trampoline, which is a rubber plate, rubber sheet that is hooked at all its ends, and you can jump on it, and that becomes a two-dimensional problem where you have position of the rubber sheet dependent on both x and y as well as time.
So I just wanted to point out, don't worry if you don't understand these partial differential equations and ODEs and PDEs and example that Supreet is talking about. Don't worry, you just be aware that such a thing exists. You can always go back and look up and learn how these equations, what these equations mean, how they are framed. So for each domain, it will be a different partial differential equations like Supreet will talk about. So essentially what you need to understand is partial differential equations, which is represented by dou, are used for representing two or more independent variables of a particular physical quantity. It could be a motion or a magnetic field or electric field or anything, or a stress kind of thing. It can change with the time, it can change with the temperature. Those kind of physical phenomenon you have to represent using PDEs. If it is very simple, only one variable, some position changes or some quantity changes only with one variable, then it is only, you can represent it using only ordinary differential equations. Okay, that's all you need to understand. Rest of it is very detailed, so don't worry if you don't understand. If you understand it well and good, it's great. Yeah. So that's all I just wanted to point out. Don't worry about it. So Supreet, you can continue. Yeah.
Yeah. Yes. As Sir just mentioned, you have each of the fields. I mean, you have different phenomena in each of, like for example, fluid mechanics. You have Navier-Stokes equations. You have, if you look at heat transfer, you have heat diffusion equation. Or if you are in mechanical engineering or civil engineering, you have stress equation. Or if you are studying physics, for example, quantum physics, you have Schrodinger's PDE. So this slide just shows some of the important equations in each of those fields. So as Sir said, if you don't understand this, it's okay, and you can write to us. We can help you. We can provide you with more resources where you can explore more about these things. So FEM can be used to solve set of equations like this. That's the takeaway we are looking for.
So right. FEM is not some magic. It actually uses some mathematical tools, I mean formulations and modeling to simulate the physical phenomena, whether it is heat transfer, whether it is stress, or whether it is heat or magnetic flux density changing or electric field. Any such things, FEM can be used in all these domains. Yeah. So just understand that point. That's all. Okay.
Yes. So you can model the phenomena in nature using PDEs, but what actually happens is very few equations are solved using analytical solutions. So analytical solution, meaning of that is, for example, if you have a quadratic equation, you will all know that famous b plus minus root over whatever that formula is there for quadratic equation. You all know that, right? So such a formula exists for some of these PDEs, but the set of PDEs, the set of solutions, the set of problems where such a solution exists is very limited. So as a result, we need a robust, more approachable method, and FEM is that method. And the other reason why we need FEM is some of these equations, which which we didn't put them, but yeah, for example, if you look at Navier-Stokes equation, uh, this equation is very famous for being nonlinear. So don't worry about this nonlinear term. We have a slide for that. But essentially, when we have nonlinear equations, even analytical solutions fail. Analytical methods also fail. And as a result, we need FEM or FEM-related tool for analyzing those equations. So the FEM provides a very robust methodology, meaning it's the core of the FEM is actually simple. But if you look at the type of applications, the type of geometries you can apply to, it's huge. And as a result, most of the academic and industrial companies, they all rely on FEM to get accurate analysis of their product, or if they're doing any research, they use FEM and then get their job done. So this is a typical workflow of the FEM. So essentially, first thing you do is you import a CAD model. Say for example, some of you are analyzing a frame or a chassis of a automobile. So you would import that model first. Then you would do something called defining properties and meshing. For example, some of the elements of your frame could be iron, some of it could be aluminum, or some of it could be fiber, etc. So all these materials you have to define. Then you mesh. We will look at a slide for what meshing means. Then you apply boundary conditions. Boundary conditions are those external constraints that you impose on your model. For example, so on this chassis, so chassis is always on the floor, say. So that could be one of your boundary conditions. And once you do this, there is something called assembly. So FEM at a very high level is you break down this complex geometry into smaller geometries, and then you assemble all these tiny problems and then solve them simultaneously. That's what is called assembly. We'll also look at what that means in a later slide. Then we do post-processing, where we look at results, where we look at, for example, for the chassis, we look at if the vehicle is going at so and so speed, what are the stresses on the chassis, or what are the displacements. So using these stresses and displacements, you can make a judgment whether you need any reinforcement for the chassis, or things like that, or whether you have over-designed it, you can remove some of the material, things like that. All right, so meshing. So meshing, as I said, you can have a really complicated geometry for some product you are making, right? And FEM, the meshing breaks that down into large number of familiar shapes. For example, if you have a really complicated curve, you can approximate that curve using a large number of line segments. So if you have a 2D surface, you can approximate that into this either triangular or quadrilateral shapes. And when you go to 3D, you can either have tetrahedral or hexahedral, or there is something also called prismatic elements. So your complex geometry is broken down into tiny, smaller, familiar shapes. And then your governing equation, for example, say you are solving for stress. You can apply your governing equation over each of these cells. And finally, when you collect all these equations over all these numerous cells, you get what is known as an assembly, which is then solved. So for example, here we have shown a plate, a very thin rectangular plate, and we have meshed it using tetrahedral volumes. And you can see, for example, if this resolution of breaking down is not enough, you can go for more number of cells, which will help you get more accurate results. So any you look at it will usually give you something called mesh statistics. So you can look at what are the how many nodes are there, how many edges are there. Some meshing software can also tell you if there are any problematic cells that you need to avoid, that you need to remesh, stuff like that.
Basically, meshing is nothing but you are dividing the entire geometry, whether it is a flat plate or a complex a part which has very many curves, fillets, or some hole or anything. You're breaking that geometry into parts, is small parts, like Suprit showed in the previous slide as elements. So these are called elements, and each of the divided elements. And how is this done? Basically, nowadays all FEM packages have an algorithm which will understand the geometry, the boundaries of the part, and accordingly it will create the mesh, and it will provide how many mesh elements are available, and that's how it displays the statistics. I mean, what type of elements are used, and the number of tetrahedra, 3105 in this particular plate, divided into elements, and volumes. Well, of course, one number of volumes is equal to number of tetrahedras, so that is why the number is the same, 3105. The number of edges. Edges is for each of the element, you see it is defined by edges and vertices, nodes, which is called. So the nodes are 6510 and edges are 336. So that's how it calculates the algorithm works to divide the whole geometry into these small elements. So this is an essential part of finite element. So this is what is called an element. Each of the minute divided quantity, and the equations are applied to each of these elements, and progressively you calculate from the known boundary condition to the end of the for all the elements, so that you get the values computed for each of the elements across the geometry. And then in the post processing, depending on the values, color coding is done. Like, if the values is high, you color it as red, and the values are low, you color it as green. That's how you get a colorful post-processing image, which Suprit will show in the next slide. Yeah.
So this is as I showed in the workflow, first you import the model, you mesh, then you apply boundary conditions, right? So once you mesh, then you apply boundary conditions. So as I said earlier, these are external constraints imposed on the model under analysis. So these are must, because if you don't specify these, the problem becomes undefined. So for example, let's say you have a cantilever beam, right? So your FEM must know what are the constraints on that cantilever beam. So cantilever beam is held at one of its ends. So the way you represent that is via a boundary condition. For example, you might say the displacement at the fixed end is 0, right? And so the boundary conditions like this, where you are mentioning the value of a dependent variable, is called Dirichlet condition. For example, you may have a heat analysis where a certain part of the object is maintained at a constant temperature. So for example, that becomes a Dirichlet boundary condition. So this is just a nomenclature for categorizing different types of boundary conditions. So there is a Dirichlet boundary condition where the value of the variable is given. Similarly, there is something called Neumann boundary condition where the derivative of the variable is given. So for example, if you look at same cantilever beam, the fixed end has a Dirichlet boundary condition. The other end, you can specify a Neumann boundary condition, which essentially means there are no stresses. Other way also looking at it would be there are no tangential stresses on the other end. So other boundary condition is a linear combination of both derivative as well as value of that variable, which is called Robin boundary condition. So you can have some parts of your body under analysis may be subjected to Dirichlet, some of those may be subjected to Neumann, and so on. So once you specify these boundary conditions, then your problem becomes well defined, and then we can start what is known as assembly. So I'll just go through a quick example of what this assembly means. Before that, let me put up another poll. No, not there, not yet. Yeah. For assembly, understanding assembly, just consider a simple problem where you have a beam fixed at one end and it is under axial force. So the P we have shown here is the axial force acting on the right side of the beam. And so the way this beam is represented is also shown here, where we have broken down the beam into 4 nodes, which translates to 3 edges. So if you look at just one element, for example, E1, you see there are so each element will undergo some displacement. The displacements are represented as U1 and U2 here, and it's an element, so there will be forces on that element as well. And if you use the basic stress equal to strain times Young's modulus formula, you get what the force is on each of those ends. So that is what I've written here. And so you apply the same equation for each of those modes, each of those elements, right? So this is the F1 superscript E equal to K superscript E, U1 minus U2. This is the force at node 1. Similarly, you get force at node 2. And if you extend it, if you write it for all the nodes, you get a set of equations. And because these are, these are simultaneous set of equations because the nodes are interrelated. Each node is a part of different segments. For example, E1 and E2 share a node. As a result, when you apply the stress equation, the displacement between E1 and E2, the node at E1 and E2 will appear in both the equations. And as a result, it becomes a simultaneous set of equations that you have to simultaneously solve. Right. So this K is usually called stiffness matrix, and so applying the PDEs at all the elements and collecting all the equations and putting this in a K U equal to F, which translates to AX equal to B, is known as assembly of the equations. So we will now look at the application of this process. So now let's look at how we can apply FEM, or we'll look at the process of FEM via an example. So when we consider that plate that I showed earlier, this plate, and what we'll do is we'll fix one of the ends of the plate and we'll apply some force on the other end. And we'll see how the stresses, the displacements are developed over the process. So first of all, we have divided, we have meshed it using tetrahedral elements. And so the left end of the plate is fixed. And if you look at the displacement, the bottom left graph, where we have shown displacement, we see that is fixed, as in it doesn't move. And you can look at the the Z value, the vertical displacement of that node, it is fixed. And as you travel along the plate, you encounter large displacement at the other end where we are actually applying force. You can also, this is the post processing of the results. You can also look at what stresses are developed in the plate. So you will be familiar with von Mises stress which can be used to understand whether the material breaks down and what conditions. And you can, for example, we have plotted those that here. So you can see there are high stresses at the end that is fixed, and there are low stresses at the other end, which is to be expected. So as another example, we will look at a heat distribution problem.
So basically, for the stress example in a plate, you have seen the stress distribution as well as the displacement. So both of these are done using the finite element analysis. As you have seen, the procedure is applied and mesh is done. So you might want to also say, Supreet, how we did which software or what application we used.
Yes, sir. Yes. Yeah, so there is a software called SimScale. The link to the website will be provided at the end of the presentation. You can all go to SimScale, create an account. If you register it, you will get 10 free simulations. So you can just get a feel for what this workflow looks like. You can consider some problems and try to solve them using FEM.
Yeah, very popular web-based finite element simulation software for multi-domain. Actually, not just for stress. You can also use it for many other multi-domain kind of FEM simulations. The thing about it is you don't have to download and install. It is just you have to just create an account and start using the free version, which is, I think should be useful for you. So you can try it out. Simscale.com is the website. I'll post it in the Q&A. You can try it out.
So as another example, we'll look at what the temperature distribution will be in a plate that I've shown with the hole here. So for example, the top end of the plate is maintained at room temperature. Sorry, it's at 0 degrees Celsius, and the bottom end is maintained at room temperature about 60 degrees, whereas the hole is maintained at about 100 degrees. So when you have a complicated problem like this, you can use FEM to solve. Right. So for example, it's very difficult to understand what the distribution will look like. So let me show the result of that. Yeah. So again, this plate was also meshed using tetrahedral elements. You can look at some statistics here, and this is the temperature distribution you see. So for example, the blue, and we have put a Dirichlet boundary condition, meaning all the boundary conditions here all are fixed, and you can see the top end is all elements of the top end are at 293. There's a mistake here. Sorry, this is not 273. This is 293. So mistake from my side. Sorry. And then you see the bottom end maintained at 323 something, and then you have the hole that is maintained at 373. And so you can sort of, if you think hard, you can try to guess that as you go from, say, top end towards hole, the temperature gradually increases, and which is what you see here. And you can have, like for example, we've only added fixed boundary conditions, fixed temperature boundary conditions. You can try adding, say, for example, natural convection, or you can have forced convection, which will then change the nature of the solution. So to do this analytically would be, for each of these boundary conditions, you would have to actually find analytical solutions which will have completely different form each time. But in FEM it doesn't happen. It's just a change in number or addition of a condition, and the whole process remains same. You don't change anything else, just the boundary condition. Right, sir. So I'll now hand over to Tangirala. Sir, you can take it.
Yeah, thanks, Supreet. So we will now look at, you have seen now the stress example as well as the heat transfer example. Now we will look at electromagnetics. So we'll start from what are the governing equations in electromagnetics. And Yeah, so these are all called Maxwell's equations. Like we told you in the beginning of the webinar, all these phenomena are encapsulated into PDEs, partial differential equations. So Maxwell's equation, all the governing equations for electromagnetics finite element method model are based on Maxwell's equations. How do they look like? They look like in the table, like the Gauss's law, which is the inverted triangle symbol you see. It is called del operator, and del dot is a dot vectors. All these are vectors. Del is a vector. D is a capital. Bold letters are vector physical quantities. So when they do a dot product of the displacement, electric displacement field is equal to the free charge density. So this is Gauss's law. We'll look into each of these, what it means in the next few slides. So bear with me. So it states that electric charges actually emanate from point charges. So these are all basically from electric field. And Gauss's second law is the magnetic. It says that basically the magnetic lines emerge. Not as a loose-ended thing. It is like a loop. The magnetic lines are always in a loop. They emerge from North Pole and end at the South Pole. So that's how this equation represents. States that the divergence of the magnetic flux density is 0. So no magnetic monopoles. Like you cannot create a South Pole only magnet or North Pole only magnet. Any magnet, even if you break it down into pieces, each of those pieces will have North and South Pole. Okay, that is the explanation for this Gauss's law, which is encapsulated into this del dot B is equal to 0 equation, which is a partial differential equation. I'll show you what that inverted del means. And next is the third law is the Faraday's law, which relates the curl. The dot is called the divergence, and dot product of vector quantities is called divergence, and the cross product, which you see in the third Faraday's law and Ampere's Maxwell law, is the curl of the vector quantity, vector product, dot product and cross product. Okay. So the third Faraday's law relates the curl of electric field to the time rate of change of the magnetic field. So minus dou B, B is the magnetic flux density and E is the electric field. So the rate of change of magnetic field produces electric field. Okay. So as you saw in yesterday's motor thing also, so we pass current into the coils and it generates a magnetic field, rotating magnetic field. That's what rotates the rotor. So basically, that's what this rate of change of magnetic field produces electric field. It is actually used in generators also. This is the principle of generators. And the Maxwell's Ampere's law, the rate of change of electric field produces the magnetic field. H is the magnetic field, relates the H is magnetic field, and D is the displacement current. The electric charge is producing the electric field. So as you can see, both the electric field and the magnetic field are kind of coupled. The rate of change of one thing generates or gives rise to the other quantity. The changing electric field produces magnetic field, changing magnetic field produces electric field. That's what these laws are meaning. That is the interpretation. Okay, so you just have to understand that particular. Supri, you can go to the next slide. Yeah, now we look into Gauss's field. Like I mentioned, the del operator is actually a three-dimensional vector quantity. So ijk represent the three dimensions in the XYZ coordinate system. And I is the unit vector in the X direction, J is the unit vector in the Y direction, and K is the unit vector in the Z direction. So the rate of change in the X and Y and Z directions are represented by dou X, dou Y, and dou Z. Okay. And rho is the electric charge density. So that is the representation of del dot D is equal to rho. And as you can see, it expands into dou dx by because electric field can be present in 3 dimensions. It is not just in 1 dimension or 2 dimensions. It can field is 3-dimensional. So as you can see, the positive charge, I mean, it is only a 2D representation on the screen or the paper. So the vector field, the field vector is actually going out from the positive charge and coming into for the negative charge. So that is how the direction of the vector represents what charge type it is. Just like north and south pole in 2 different places. But then they don't loop. I mean, they are like, what it says is electric field lines start and stop on electric charges. So they start and emanate or get into the charge depending on what type of charge it is. But you draw closed surface around it, any electric field coming out of it must be due to the electric charge trapped inside. So if you draw a shell, the electric lines come out of it. Are they due to the electric charge only? So as you can see, they don't loop. They are like individual field vector lines. Okay. Next slide. Now we look at the Gauss's magnetic field. Like I said, what this equation means is the field lines never start or stop. They always form closed loops. Okay. So in the figure 5.49, you can see a current carrying conductor generates magnetic field. So this is in the whether the field is in clockwise or anti-clockwise direction depends on the direction of the current. If it is going up, the direction of the current is upwards, then it is in probably anti-clockwise direction. If it is downwards, I mean from top to bottom, probably the magnetic field will be in the clockwise direction. So the field direction also changes according to the direction of the current. So that is why they are all vector fields, vector quantities, electric field and magnetic field. And in the other 5.50 picture, as you can see, the current carrying conductor in a 3D, you will see the loops. I mean, it forms a circle, the magnetic field. So current carrying conductor produces magnetic field, and changing magnetic field we'll see later that also. So in the magnet also, the magnetic lines emanate from north pole and end in the south pole. So that's how the magnetic lines are. Even in a solenoid, there is a north and south pole. So lines emerge from north pole and end in the south pole. Okay. I mean, I don't know if you have any questions, you can post it in the question and answer tab. Yeah. Then we come to the Faraday's laws of induction. Induction is when one field creates another field, like changing magnetic field. Dou B by dou T, what does it represent? It represents the change of magnetic field with time. Okay. So if the field changes, there is a change in the magnetic field that results in electric field. That is what these equations mean. And all these equations are used in the simulation of electromagnetic simulation. Any system that you want to simulate in electromagnetic, these equations are used. And well, as Supreet pointed out, then you apply the boundary condition. The same procedure is used, except the governing equations are different here. Okay. So like in the picture that I depicted, 11.4, if you move the magnet up and down, then only you see the needle moves in the ammeter. That means there is a current, galvanometer. That means there is a current flowing in the circuit. If you stop moving, then there is no current, right? What does that mean? That means the changing magnetic field only produces electric current. If there is no change in magnetic field, there is no current. Okay, that's all it is. Okay, simple enough explanation. So this is an experiment that you can probably visualize and relate to. Okay, so that is what Faraday's laws of. Then we look at the fourth equation of Maxwell's law. So this is Ampere-Maxwell law. This is the inverse of Faraday's law, which states that magnetic field is created by either an electric current or a changing electric field. So here the current density, H is, like I said, is the magnetic field. and J is the current density, and D is the current displacement. I mean, rate of change of current displacement. So both J or dou D by dou T both produce the magnetic field. Like you saw, the current carrying conductor doesn't have to move. Like even if it is static, it produces magnetic field, right? So that is represented by J. And if the electric field is changing with time, that also produces magnetic field. So both are encapsulated in this equation. So basically, Faraday found that the induced EMF meaning changing magnetic field, how much, so if the magnetic flux is phi here, and there are a number of turns n, this is actually a generator which produces an EMF, right? So the changing, the rotary motion of the generator produces magnetic field, that in turn, which keeps changing, produces the EMF, electric field. So that is what this equation represents, and it depends on number of turns of the coil that is in the generator and the magnetic flux, and that is the rate of change, del phi by del T, which is the rate of change of magnetic flux times the number of turns in the solenoid or in the generator produces the EMF. And then Lenz's law states that the induced EMF will be in such a direction as to oppose the change. That is why you see the negative direction. So the induced EMF is always opposes the change in magnitude of the flux. Okay, that is Lenz's law. So now we covered all the 4 Maxwell's equations which are used in the electromagnetic simulation. Okay, now we will look at some examples. Suprit, next slide. So again, the same thing what I mentioned earlier. Changing magnetic field creates an electric voltage, which is electromotive force or EMF. So you need change, like I said, dou B by dou T is the changing magnetic field, right? And the faster the change, more the voltage, the magnitude. All that is encapsulated into that equation, phi by U. And it opposes the change, which is Lenz's law. So all 3 put together is in that one equation. Now we will play one video explaining this Faraday's law, because electric motors are all based on Faraday's law. And Faraday actually, proof of concept, I mean, he developed the first AC motor. Okay, actually, yeah, it was a DC motor. Then Nikola Tesla made the AC motor commercially viable. So we'll just go through this video and just pay attention to the video for a couple of minutes. It's only a 3-minute video. It'll explain how the magnetic field is generated. Yeah.
Today we will discuss the concept of Faraday's law of induction. Faraday's law states that the EMF induced in a coil is proportional to the rate of change of the magnetic flux through the coil. Let's consider a situation. Have you ever seen the metal detectors at airports? Do you know how they work? They follow the same principle that is followed by transformers, generators and motors, which is Faraday's law of induction. Let's talk about Faraday's law in detail. Faraday's law of induction states that the EMF induced in a coil is proportional to the rate of change of the magnetic flux through the coil. Magnetic flux is the number of magnetic field lines passing through a closed surface area, and it is expressed as, here B is the magnetic field through the closed surface of area A, and theta is the angle between the magnetic field and the normal to the plane of the loop. Consider a coil of wire of n identical turns, each with magnetic flux of. The induced EMF in the coil is given as, in the formula, is the induced EMF, and is the change in the magnetic flux in time. Thus, the EMF will be induced only when there is a change in the magnetic flux. If the magnetic flux is constant, then there will be no induced EMF. Due to this induced EMF, a current will be induced in the coil of the wire. The direction of the induced current is determined by Lenz's law. According to Lenz's law, the direction of the induced current in a circuit is such that it opposes the change in the magnetic flux. Let's talk about some potential common mistakes. Do not think that there will be an induced EMF only when the magnetic field is changing. The magnetic flux through a loop depends on 3 parameters: the magnetic field through the loop, the area of the loop, and the angle between the magnetic field and the normal to the plane of the loop. If any of the 3 parameters is changing, there will be a change in the magnetic flux, and so the EMF will be induced in the loop. Let's take a real-world example. Consider a 200 turns coil of radius 5 centimeters that is placed in a changing magnetic field, such that the magnetic field is perpendicular to the coil. Calculate the EMF induced in the coil if the magnetic field is decreasing by 5t in 4s. The EMF induced in a coil is... Substitute the flux expression. Here, the magnetic field is changing with time. Therefore, the magnetic field is perpendicular to the loop, which means that the angle between the magnetic field and the normal to the plane of the loop is 0 degrees. Substitute the given values and calculate the EMF. Summing up, we learned about Faraday's law, which states that the induced EMF in a coil is directly proportional to the change in the magnetic flux through the coil, and the direction of the current induced in the coil is in such a way that it opposes the change in the magnetic flux.
Well, yeah, thanks, Supreet. Go back to the slide. I hope you understood in more detail what the video was mentioning. Fine. So how does this all relate to? So I just wanted you to give some physics behind this electromagnetism. So you all must have heard about electromagnetic waves. These are actually both combined, electric and magnetic fields interacting together. Like, for example, the light you see, even the sunlight or any light, but normal tube light or wherever you are, they all travel in straight lines, and each of these light is an electromagnetic spectrum. Like, these waves have the magnetic field and the electric field oscillating in perpendicular planes in 3D. So in 3D, you can imagine XY plane. If the magnetic field is changing in the X plane, the electric field will be changing in the Y plane, and Z will be the direction of motion of the light. And as you all know, light travels at speed of 3.010⁸ meters per second. So that is like 300 million meters per second it travels. That's the speed of light, which is c. And so obviously these are all waves, right? And every wave has a wavelength, and you talk about frequency and wavelength. So this spectrum depicts what light and radio waves look like, what is the frequency and all that. Even the visible light, our eye perceives only a very tiny fraction of this electromagnetic spectrum. We can't see the radio waves, microwaves, or even infrared waves, but only in the region of some 700 nanometers to 300 nanometers wavelength. That is how much the wavelength of this visible light is. So on the one hand, you have the red obviously has the highest wavelength, and violet is the shortest wavelength in this electromagnetic spectrum. So longer wavelength, lower frequency, lower energy. So from the left, you see the radio waves have very high wavelength, and that's why their frequency is less. As it moves to the right towards the gamma rays, the frequency increases, frequency of oscillation of the waves increases, and the wavelength keeps decreasing. So the wavelength is inversely proportional to the frequency, and c is the constant of proportion, the speed of light. So c is equal to lambda v. Lambda is the wavelength, and nu, the v sort of thing, is the frequency. And frequency and energy are also related by Planck's equation called E is equal to h nu. And if you substitute c is equal to lambda v, you end up energy is equal to hc by lambda. And both energy and mass are also related by Einstein's famous relativity equation, right? E is equal to mc squares. So energy and mass also can change. And of course, light also exhibits particle-like behavior as well as wave-like behavior. And of course, I'm going into physics now, but very interesting topic. So these photons are emanated from when the source of that light, in that there is an electron jump from one level to the other. That's when the jump of that electron from one shell to the other results in a photon emission. And when this continuously happens, when you apply a current or voltage across a light bulb or something, this is what happens. And those electrons jumping back and forth in the tungsten filament or whichever principle, that's what produces the light, and that is electromagnetic spectrum. And for light also behaves like a particle. As you can see, the photoelectric effect you must have heard about is all based on, which proves that light also behaves like a particle. Photoelectric effect is if you impart the electromagnetic energy into photoelectric plate, it emits electrons. Electrons are ejected from the metal plate conductor. So that is photoelectric effect, right? So that cannot happen if it is only wave, then it's only a particle, right? Anyway, so these are all related topics I just wanted to touch upon, and hope you found this interesting. So because everything is related to electromagnetism. So other reason I wanted to touch upon this is we all see this, we are all living in an electromagnetic field actually. Earth has magnetic field, and light, of course, is electromagnetic. So everything is electromagnetic around us. So I just wanted you to be aware of this, okay? And yeah, so I said shorter wavelength, higher frequency, higher energy. So these are the governing equations. Okay, next slide, Supreet. Yeah, now we come to the simulation of a motor. So this you see is a mesh of, not a mesh actually, it's a geometry representation of the rotor, the entire motor, the stator and the rotor. So basically in motors, like Oscar was mentioning yesterday, you don't, most of the motors are not made as a solid. They're made out of laminates. Laminates meaning a thin plate, which is carved into they put holes in it, and that will become the stator. So when you stack up these laminates, about 50 or 100 of them, then you get a stator thing. Then you bunch them together and you make a stator. Similarly for rotor also, you make a geometry of a laminate and then stack them up and do it. The reason the plates are used is to reduce eddy currents. If there is a solid, if the stator is made of solid material, then there will be a lot of eddy currents and losses will be very high. So to reduce the eddy currents, use laminates. Laminates meaning it's like a plate sort of thing with some geometry. So here I'm showing 1/8 structure, not the entire stator geometry. It is the section of the stator geometry, 1/8 section. So outer thing is stator, and inside you can see the little gaps. That is where the windings are done. The copper coils are there. And the other part, from the center, if you see, there is a rotor. It's written, right? So you can see the rotor thing there. And that rotor has holes to hold the magnets. It can be N52 or it could be many other magnets are there. Samarium and cobalt and ferrite kind of magnets. Each magnet gives different magnetic properties. And some are, of course, costly, some are easy to make, all kinds of things are there. So these magnets are placed, and this is the rotor which rotates, and stator which is stationary. In between them is a small air gap, very small, like less than 1 millimeter, probably around half a millimeter. You should visualize how much millimeter is. So half of that is the gap. That's where the rotating magnetic field is generated, and that makes the rotor move. So this is the given this geometry, we need to mesh this. So as you can see, as Supreet pointed out, first step is to create the geometry, right? So we created geometry for the stator, rotor, the coils, and we also identified the material. The stator is made up of iron, the windings are made up of copper, and the rotor is also made up of iron. And the magnets, of course, are magnets. So there are material properties of each of these materials are also assigned. So this is the basic first step of the FEM simulation. Okay. And with this, and of course, air is also there, right? You can see the air gap. So that air is also one of the materials. Okay. So that is also represented here. So now we have a complete geometry of the motor simulation. Okay. Including the materials like air, copper, iron, magnet, everything. So this is what you first create in our PiCADS motor application. You create the stator, you create the rotor, and you specify what kind of magnets. All these are assigned and taken in. This geometry is the output of all that pre-processing. Okay, this is the first step, as you can see, as the for the FEM simulation. Now we'll get to the second step. Supreet, you can, yeah. So in this diagram, I'm showing the output as well as the mesh across all three elements, the rotor, stator, windings, everything. If you can zoom in or make your screen maximized view, you can see the mesh also, very fine lines. And the colors you see are the Tesla, the magnetic field flux density, what we call as the flux density. So there is a shaft, there is a rotor hole, and there is a magnet, and there is also stator. So all these, as you can see, the magnetic lines, the flux density is very high in the regions close to the magnets, and that is also impacting the stator magnetic flux, inside the stator magnetic flux. And using this, I mean, this is a very uniformly distributed magnetic field. And this is what will give an indication of how powerful the motor will be. I mean, the intensity of the magnetic field and the geometry and everything put together. Because the geometry will dictate how big or small the motor is. And when you divide, because this is a 2D finite element method, because each of the stator and the rotor are made of laminates. So if you do simulation for one laminate, it is equivalent to doing the entire 3D, because you stack up the laminates all together, right? So if we can and the 2D finite element methods is also not so expensive or time consuming. It because of lesser number of elements as opposed to a 3D element. 3D element, of course, you have more nodes, more elements, that takes more time. Okay, we'll come to that later. So I hope you got an idea of how to simulate the motor, and this knowledge or information will help you use our PiCADS software motor, PiCADS motor simulation software, what happens behind the scenes. Yeah, so we'll be able to understand what goes on behind the scenes. Okay, so I hope yeah. So the magnetic flux density is always measured in Tesla. Tesla is Webers per square meter. It's Weber is the unit of magnetic field density. So density is the field intensity divided by the area. That is what is flux density. That is called magnetic field is measured in Tesla. Okay. Next. So other examples I want to show in 3D, displacement of an aircraft wing under load. So like Supreet mentioned about the beam, the plate, and you fix the plate on one end, Other end you apply the load and you see the deflection. Similarly for aircraft wing, you could say it's a different geometry, right? It's not like lid. It tapers down. It is wider at one end, less wider or thinner at the other end. So you can simulate this also. This is an example depicting how the displacement happens. So obviously the red indicates maximum displacement, which is at the other end. The fixed end actually doesn't move. It's only 0 meters thing. And that is the aircraft wing. And of course, the thermal example is the IC engine. This thing, if you see a motorcycle, this is how with the fins and all that, the motor engine looks like. The fins, as you see the plates around the engine, are designed to take away the heat, because you're increasing the surface area with each fin, and more the surface area, more the heat will get taken away or dissipated. So that's how the cooling mechanism happens without any external fan or cooling or whatever. So this is basically a convective heat transfer from the fins to the air. So this is one example. And of course, where the engine is, obviously the heat will be more, and rest of the places it will be relatively cooler. Yeah, that's what this example is. So basically what we are saying is you can use FEM for any geometry, whether it is 2D, 3D, or any complex part like a motor, or even in this now this slide, it's of a bridge. This is a stress analysis of a bridge, one measure stress, and all the red parts, as you can see, when the load is applied on the bridge, where the stresses will be. So simulation helps you before making the bridge, where the stresses will be, so that you can redesign it to lower the stresses, because you want, after all, the bridge to be safe. I mean, it should not crash. It should not. There should not be any failure point, right? It should not crack and fall down. So you can identify where are the vulnerable points in the bridge, the failure, using simulation, and accordingly change your design or put some other way to deal with the higher stresses, so that the bridge can last longer and it will be safer. So this is what simulation will help you. And why are we doing, why will we want to do simulation of motors, is to understand the efficiency of the motor. How do we calculate the torque speed curve? What should be the ideal operating point of the motor? All these things before you make the motor itself, manufacture the motor. A simulation will help you design that motor for maximum efficiency, and also it can tell you what will be the cost. Simulation also nowadays tells you what should be the winding, how much copper wire you use, how much of material you use. So you can calculate the cost that you can incur, that you will incur for a particular motor design. And if that is something out of range, you can go back, change the material, or the design, make it smaller or bigger, and play with it, so that you get your ideal motor that you want an application to use, or a vehicle or something, or a grinder or a fan or whatever. So that is the purpose of simulation. Okay. So in summary, what we are saying is FEM involves differential equations, and there are two types of differential equations: ordinary differential equations and partial differential equations. Ordinary differential equations have only one independent variable, example time, or it could be x or y, z dimension, one dimension. And partial differential equations, invariably you have space in x, y, z, the three-dimensional space, and time. So two or more independent variables, if you have to deal with, then you have to go with the partial differential equation. And derivatives used, ordinary differential equation are represented by dy by dt. Rate of change of displacement with respect to time is the velocity, right? So that is represented by dy by dt. And partial differential equations are represented by dou operator, dou symbol, which is actually a Greek letter, dou u by dou t, or dou u by dou x, or dou u by dou y. All those rate of change of that, whatever u is any quantity, right? It could be heat, it could be magnetic flux, it could be electric field, it could be magnetic field, anything. So that change of that quantity with respect to time, with respect to space, is the partial difference, partial derivatives. And physical scenarios, you can represent motion of a pendulum using ODEs, radioactive decay, because it only depends on time. Radioactive decay depends only on time, right? Half-life, as we call it, uranium and other elements. And simple electric circuits also, you can use differential equations to govern, to understand the phenomenon. But when it comes to complex systems like heat flow, wave propagation, sound, light, fluid dynamics, you need partial differential equation, or even electromagnetics, like we talked about Maxwell's equations, right? And of course, ODs are easy to solve, and PDs are generally much harder to solve because you have to follow the finite element method 5 steps. Okay, first is the geometry creation, second is the meshing. Meshing involves different types of elements. It could be triangular, it could be tetrahedral, depending on the type of element that you use. You have the choice. Well, the type of element, if it is more complex, it takes more time. Like if it is a simple triangular thing, then it will lesser number of nodes, lesser number of elements results in lesser faster simulation. If the number of nodes are more, or at the same time, when lesser number of elements and nodes give you less accurate results. If you want more accurate results, you have to create more elements, more nodes, and that's when you create. But then it takes longer time, because more elements means more time, simulation time, right? Because the solver goes through all these iterations and has to solve for so many more elements. And then, of course, put the boundary conditions and all that, and put all things. And all the other steps, like, putting the equations together, solving, and all that happens behind the scenes in the simulation software. So you don't have to write all these equations. All we have represented is for your understanding only. All the Maxwell's equations, solvers, and all that are already built into the application. So when you invoke the solver, it automatically, but then you have to define the geometry and assign the materials. Like you have to define the problem that has to be solved, and then given to the solver to solve it. So that much you have to do in simulation software. Any simulation software, not just PiCADS. It could be ANSYS, it could be Altair, it could be SolidWorks, anything. So finally, next slide, please. Yeah, we briefly talked about linear and non-linear. So sometimes, we tend to, for example, in deformation, there is also elastic region and plastic region, right? So if your deformations are in the plastic region, linear FEM doesn't work. You have to go with non-linear FEM. And geometry for small deformations, it is fine. For large deformation, we need non-linear FEM. What do we mean by non-linear is it takes the dynamic material properties, or the dynamic state of each of the deformations into account to calculate the next elements solver. So it takes a lot of time, and more complex equations will be involved as opposed to a linear equation. So with that, I think, yeah, solution method for linear FEM is single step direct solution, but for non-linear FEM, it is incremental and iterative. So for example, Newton-Raphson method and all that. So like I said, linear FEM is computation cost is low and it is very fast. And so it takes less time. Less time means less cost. And the non-linear FEM is high and slower because the cost is high because it takes more time to solve. Because many more iterations need to be done to arrive at to take into account the non-linearities in the system. So at that, I think we wrap up this session. Next slide, Supreet. Anything else? Yeah, that's it. So these are the references. We'll share these references in the follow-up email that we'll send you. Okay. So you can go through these videos. There are lots of nice videos on YouTube explaining finite element methods. A beginner's guide is one of the very interesting thing. And simscale.com, if you want to play and do some simulation, other than electromagnetics, because PiCADS is only designed for motors. So electromagnetics and all that, that you will get a chance to play with in the next session when we'll do the demo of PiCADS for you. Okay, so that is scheduled on day after tomorrow, which is 30th. Okay, 30th of November, same time, 6 to 7:30. But before that, if you want to do some simulation, you can go to simscale.com and try out a simple simulation like Suprit mentioned, define a plate, just some simple geometry, and put some boundary conditions and run the simulation and see what the results are. Okay. It's up to you. You can do thermal, you can do stress analysis with whatever. So with that, we come to an end. If you have any questions, please email us at picads.course@pilabs.in. Okay. Thank you all for attending, and I hope you learned something in this session. What FEM is, how it works, and what are the governing equations behind it. It's all math and calculus. I mean, partial differential equations and differential equations, and even the vehicle dynamics that you saw in the first session is all about physics and math. So physics, math, and calculus, these are three subjects I think you need as an engineer, you need to learn or be interested at least in these three subjects all through your life. Otherwise, as an engineer, you will not be able to create anything or simulate anything. Even simulation is also becoming a big part of every engineer, be it mechanical engineer or electric or electronics engineer. Okay. So with that, we come to an end, and you post any questions anytime. So thank you all. If you don't have any more questions, we'll end the session.